Alright students, so here we are for section 3.5, our first video recorded lesson. So I'm going to scroll down first on these notes to the second page to get our goal for the day. What we're trying to do here is we are trying to sketch graphs of functions using what we know about calculus to model their behavior. So before we do that, we're going to learn one more thing here. This section is going to tie together all of the things that we've learned about the first derivative, so increasing and decreasing, and the second derivatives, concave up and concave down. And we're also going to use some more algebra techniques like looking at whether or not the function is odd or even to tell its symmetry. So let's take a look at the first question here. How can we tell if the function is odd or even by looking at the equation? Well, this is technically easy to do, but there's usually a little bit of computation involved. And what we're going to do is we're going to go ahead and evaluate the function at f of negative x. So we're going to plug in negative x there and see what we get. And if when we do that we get back the original function, this means that the function is even. And similarly, if we evaluate f at negative x and we get negative f of x, so all the signs are reversed, then f is odd. And so let's take a look at some of these graphs. So here we have the graph of x to the fourth minus 4x squared. And this is an even function. You can tell by looking at it because it has symmetry over the y-axis. You can also tell because the powers on the function are all even powers. And if we look at the value of f evaluated at x and evaluated at negative x, for all x values, they're the same values. So this is even by definition, and it's even by symmetry. And now if I take a look at an odd graph here, x to the fifth minus 4x to the third, you can see that the function values are different by a negative sign, but they have the same amplitude, and we have symmetry around the origin. So flipping back to the notes then, we can tell that a function is odd or even by plugging in negative x and seeing what we get from the formula, or we can tell by looking at a graph of that function. If it's symmetrical across the y-axis, so that's reflection symmetry, then it's an even function, and if it's symmetrical around the origin, so if that's the 180-degree rotational symmetry, then it's an odd function. We're going to use this to help us graph functions later. So to do some quick practice, let's scroll down to these next examples here, example 11, and we can look at these functions, and if we plug in negative x, we can determine if they're odd or even from the formula. So for part A here, let's go ahead and calculate p of negative x, which means that we're going to plug in negative x everywhere we see an x in the original formula, so we get negative x cubed plus negative x plus 1. And then if we simplify this and we get either negative p of x or just regular p of x, we'll know if it's odd or even. So let's go ahead and simplify this. So we can, this is an odd function itself, so we can pull out the negative there because negative x cubed is negative x cubed. That makes sense. And then this is going to be a minus x right here plus 1. And then let's take a look at this. Is this the original function p? Nope, we have some negatives here that we didn't have before. So it's not p of x, which means that it's not even. And if we undistribute a negative here, will it look like p of x? So let's go ahead and take a negative out here, and we get x cubed plus x minus 1. Now that is not x cubed plus x plus 1, so it's also not odd. And that means here that this one is just what we would say it's neither odd nor even, or on WebWork you would just write neither. And so if we take a look at a graph of that function, we can see that it's not symmetrical across the y-axis, because if we flip it here, it doesn't land on itself. And it's not symmetrical about the origin, because it would have to go through the origin. If we rotated this graph, it would look like it changed. So, and if we take a look at these values here, you can see that they aren't the same number, and they're not the opposite number. So they're neither odd nor even by the formula and by the symmetry in the graph. Now let's pop back and take a look at this more trivial example. So for f of x, for part B here, we're going to take a look at f of x is equal to 5, which is just the constant function. Now, if we evaluate f of negative x, that's still just 5 because there's no x involved in the formula. And that means that f of x and f of negative x are the same thing, which means that this is an even function. Now, we should see that in the graph pretty easily. You can see here that f of 5, or f of x equals 5 is just a horizontal line, at y equals 5, and the values are always 5 because that's all the function is, and therefore it's an even. Shoot, I messed up the video here. Sorry about that. Let me explain. We just finished part B, and now let's take a look at part C, and we're going to see the example nearly completed here. So what I've done for part C here is I'm calculating g of negative x to determine if it's odd or even. And so I'm going to plug in the negative x everywhere I see the x. And in the second step you see that done. And in the third step I've started to simplify that where I have negative 4x cubed plus x divided by x squared plus 1. But if we do some tricky distribution here, let's try to plot a negative out of the top there. What do we get? Then we get 4x cubed minus x, all divided by x squared plus 1. And we can write that negative just out front. And then we get 4x cubed minus x divided by x squared plus 1. And that is just our g of x there with the negative out front. And this means that it's an odd function. Now let's take a look at a graph real quick. And if we take a look at this function, we do see that it has that odd shape, and I mean that it's symmetrical about the origin right there. If you take a look at these values, they're the exact same numbers with just a different minus sign. And I think that's enough practice in odd and even functions for now. Part D is an odd function, and you can check that on your own if you'd like. This is just a thing that you have to remember with trig, is that sign is odd, so you can pull the negative out. But we're not going to worry about that for right now. So I'll just give you a second there to pause if you want to take a look at any of that work. Okay, moving on to the next problem. So let's take a look at example 12 here. So this is an example that brings together all of the elements of what we've learned about derivatives so far. We're going to use derivatives to figure out when this function is increasing and decreasing. This is what we're going to use the first derivative for. And then we're going to use the second derivative to figure out where the function is concave up or concave down and identify any inflection points. We're going to use just a regular algebra to figure out what the domain of the function is. And we're going to use the stuff that we learned about the limits at infinity to figure out where the asymptotes are. This is a long problem, so settle in for a haul here. First of all, we need to figure out the domain. The way that we're going to figure out the domain is we need to figure out where the denominator is equal to 0 in our... So where x is equal to plus or minus 1, if we just add the 1 over and take the square root, that's where the denominator is going to be 0. So our domain here is going to be negative infinity to negative 1, and union with negative 1 to 1, and union with 1 to infinity. And we're going to have vertical asymptotes there at x equals negative 1 and x equals positive 1. To find the x and y intercepts, we're going to use a little bit of algebra. First, let's go ahead and find the x-intercepts. Remember, these are the roots. And the way that we're going to do that is we're going to set y equal to 0. So in this case, y is our f of x. So we're going to go ahead and say that 0 is equal to 2x squared over x squared minus 1. And then we can multiply both sides by x squared minus 1. And then we get that 0 is equal to 2x squared. And from there you should be able to get that x is equal to 0. So in this case, the x-intercept is at 0, which actually tells us the y-intercept as well. But we can show the work for that anyways. To find the y-intercept, you're going to set x equal to 0. So we're going to have that f of 0 is equal to 2 times 0 squared over 0 squared minus 1. So you get over negative 1, which is equal to 0. We should have already known that because our y-intercept is 0. And these two together say that this graph touches the point 0, 0, so it goes through the origin. Now let's go ahead and check if this function is odd or even. Remember, we're going to check that by evaluating the function at f of negative x. So we're going to calculate 2 times negative x squared over negative x squared minus 1. And we're going to see here that we get the exact same function back because those squareds take care of that negative for us, and we get our original f of x back, which tells us that this function is even. And that tells us that the graph is symmetrical across the y-axis. Let's take a look at that. So here's a graph of our function, and we can see that it has that shape where it's symmetrical across the y-axis. So it is even, and it does go through that point 0, 0 like we found. before we ruin the fun, let's hop back to the equation side of things. So the next thing that we're trying to find is we're going to try to find the asymptotes of this function. So there's two kinds of asymptotes that we're looking for. We're looking for the vertical asymptotes and the horizontal asymptotes, or the slant asymptote. The horizontal and the slant are in the same class. So remember, for our vertical asymptotes, that's usually where the denominator equals 0 for most of the functions that we're going to see in this class. There's some other functions like trig functions that have asymptotes, but you can also rewrite those trig functions to be sines and cosines, and the denominator, if it has cosine in it, let's say, so for secant, then the asymptotes of the secant function will be at pi over 2, because that's where cosine has its zeros. Anyways, let's get back to this function. And in this case, our denominator is x squared minus 1. So we have 2x squared over x squared minus 1. If we take a look at this denominator factors into x plus 1, x minus 1. And so we know that we're going to have vertical asymptotes at x equals 1 and x equals negative 1, which match the holes in our domain. And you can see here that we have our vertical asymptote at x equals negative 1 and at x equals positive 1. Later, when we're looking for critical values, remember that those x equals 1 and x equals negative 1 points are not critical values because they're vertical asymptotes. All right, let's figure out how we find our horizontal asymptote. So to find our horizontal and slant asymptotes, this usually has to do with taking the limit as x goes to infinity. That the function that we're dealing with is f of x equals 2x squared over x squared minus 1, and I can get the horizontal asymptote by just looking at these leading terms, the terms with the highest exponents. I can tell that the degree of the top is 2, and the degree of the bottom is 2. Since those degrees are the same, my horizontal asymptote should have the form y equals k, where k is a constant determined by the leading coefficient. In this case, it's 2 over 1, so my horizontal asymptote is y equals 2 over 1, or y equals 2, which is what we found when we did that crazy polynomial division. So y equals 2, let's write that nice and cleanly. That is my horizontal asymptote. And you can see here, I'll give you a second to pause here. Asymptote. And you can see here that we do have a horizontal asymptote at y equals 2. Ooh, I'm getting tired. I told you these problems are long because they're bringing together a lot of different mathematics. The next part of the question asks us to find where the function is increasing, where the function is decreasing, where the local maxes are, and where the local minimums are. And these are all tied together in the sense that they are dealing with the first derivative. So the first thing we need to do here is we need to calculate the first derivative. We need to find d dx of the function 2x squared over x squared minus 1. That's our original f. And in order to do that, we're going to need to do the product rule. So we're going to get 4x by taking the derivative of the numerator divided by x squared minus 1, subtracted from 2x squared. We're going to leave the numerator the same, multiply by the derivative of the denominator, which is 2x, and then we're going to go ahead and divide by the denominator squared. This is a long process to do all of this. And now let's go ahead and simplify that real quick. And we get negative 4x over x squared minus 1 squared. I'm going to give you a second here to pause so you can follow that if you'd like. And I'm just going to move that up here to get it out of our way. But let's remember that this is our derivative right here. Negative 4x over x squared minus 1 squared. So now we need to use that to make our number line that has the signs of our derivatives. And to do that, we're going to first need to break up our interval by finding our critical points and our vertical asymptote. So remember our vertical asymptotes, we already found those are at x equals 1 and x equals negative 1. We quickly need to find our critical points by setting the derivative equal to 0 and solving for x. So here I've set the derivative equal to 0, negative 4x squared over x squared minus 1 squared equals to 0. And that tells me that negative 4x must be equal to 0 because I can multiply that denominator over. And that in turn tells me that x must be equal to 0, and that is our critical point. So now let's build our number line. So we can do our number line from negative infinity to infinity, and we're doing an f prime number line to determine where things are increasing and decreasing. We need to put our vertical asymptotes on there. So we have vertical asymptotes at x equals 1 and x equals -1, and we have a critical point at x equals 0. And now we have 4 subintervals here. We have negative infinity to -1, and we have -1 to 0, and we have 0 to +1, and +1 to infinity. And now we can test points within those intervals to determine if each of those subintervals is either positive or negative. I like to organize this using a table. So we're going to go ahead and write each of our 4 intervals in here. So negative infinity to -1, -1 to 0, 0 to 1, and 1 to infinity. And these are the 4 intervals that we need to test points within to determine whether or not they're positive or negative. So something inside of negative infinity to -1 is -2, and -1 to 0 is -0.5 or -1/2, and from 1 to 2 is a 2. And then we're going to plug these points into the derivative in order to figure out what the sign of the derivative is. Now we can actually do this without completely calculating the values, so we can tell here that when we plug -2 into the derivative, we get +8 divided by 9, which is a positive number. Another way that you can think about this is if you're plugging a negative number into -4x, you're going to get a positive number. And then if you plug a negative number into this thing, well, it doesn't really matter because you're squaring the whole thing, so you're going to get a positive number in the denominator. And if you have 2 positives here, we have a positive number as well. And the reverse holds if we plug in a positive number. If you plug in a positive number to -4x, you get a negative number. And then again, the denominator is still positive because it's squared, and a negative divided by a positive is a negative number. And that reasoning holds true for both 1/2 and 2. And we know that on both of these intervals, the derivative is negative, which means that the function is decreasing. So let's go ahead and sketch that in here on the number line. I'm going to say that we have a little increase there, and an increase there, and a decrease here, and a decrease here. And that tells us that this function is increasing from negative infinity to -1, and -1 to 0. Let's check if that matches our graph. And you can see that the function is increasing from negative infinity to -1 and -1 to 0, and the reason that there's a break is because we have this vertical asymptote. And the function is decreasing on the complementary set, which is 0 to 1 and union with 1 to infinity. And again, we'll see on the graph that we have a decrease from 0 to 1 and 1 to infinity, again interrupted by a vertical asymptote. So I'll give you a second to take down some of those notes. So go ahead and pause right now if you want to write some of this down. Now we have one last question here. We need to identify any local extrema, and we do that by taking a look at our critical points, and we need to classify them. And we can see here, using the first derivative test, since it's increasing on the left and decreasing on the right, this critical point must be a maximum. So we should say that we have a local maximum at x equals 0. And if we take a look at the graph, there's our local maximum at x equals 0. Alright, so now we've come pretty far. Now we have one last question to answer, and that's the question about the second derivative, where we're trying to figure out where this function is concave up and concave down. I have to give you a warning, this algebra is pretty terrible. So here we need to figure out where the function is concave up, concave down, and if it has any inflection points. And we're going to tell that by finding the second derivative and analyzing the second derivative. So real quick, here's the first derivative, -4x divided by x squared minus 1 squared. We need to take the derivative of this using the quotient rule. Let me do that for you real quick. Yeah, so there's our quotient rule. Notice I'm taking the derivative of 4x here, and I'm taking the derivative of x squared minus 1 squared here. Whoops, we shouldn't have a squared on that. That should just be 2 because we're taking the derivative of the squared function, and then we have to do a little chain ruling here on this x squared minus 1 to get a 2x. And I hate to break it to you, but we actually aren't even going to get any zeros out of this. So let me just do the simplification real quick, and why don't you save some of your energy. So there's a simplification. We end up with this as our second derivative. And now we need to figure out where this thing has zeros and where it's undefined. Well, it's undefined where x is equal to 1 or negative 1, because those are the vertical asymptotes. And the second derivative is never equal to 0 because we have a squared here being added to 4, so it can never hit 0 because we have two positive numbers. So since these vertical asymptotes can't be inflection points, then we know that there are no inflection points because there's no places where this derivative is equal to 0. However, we still do need to make the second derivative graph to figure out where the original function f is concave up and concave down. So again, we need to put the vertical asymptotes on our number line to subdivide this interval, and those are at x equals negative 1 and x equals 1, and then we're going to do the same thing here. We're going to do test points in the interval. And in this case, our intervals are negative infinity to negative 1, negative 1 to positive 1, and 1 to positive infinity. So I'm going to put those values in a table. Here's my table. I'm doing the same thing. I'm going to need 3 rows for my 3 different intervals. My intervals are negative infinity to negative 1, negative 1 to 1, and 1 to infinity. A test point in here would be negative 2, a test point in here would be 0, a test point in the 1 to infinity interval would be positive 2. And we're going to go ahead and plug these into our second derivative. And we're going to, for all of these, like I already said, we're going to get a positive for the numerator no matter what we plug in. And in the denominator, we're going to get positive numbers when we plug in something that's magnitude is greater than 1, because if we plug in a negative 2 here, we get negative 2 squared minus 1, which is 4 minus 1, which is a positive 3. So we're going to get a positive in the denominator when we plug in a 2 or a negative 2, but then if we plug in something less than 1, like 0.5, when we square that, we get 0.25, and if we subtract a 1, we get negative 0.75, and that's a negative number. So we're going to get a negative there in the denominator in the middle. Overall, that gives us a positive, negative, positive parity on our intervals, which means that it's concave up from negative infinity to negative 1, and from 1 to infinity, and it's concave down from negative 1 to 1. So let's go and write that out. And remember that we have no inflection points. Usually our inflection points would occur where we have the concavity change from concave up to concave down or concave down to concave up, but these are vertical asymptotes, so they cannot be inflection points because they're not part of the domain. So I'll give you a second to jot some of that down if you're still taking notes. Go ahead and pause. Alright, so hopefully you've had some time to take all of that craziness in. Now, I've copied all of that information into one screen here for you. So we have our intercepts at x equals 0 and y equals 0, our asymptotes at y equals 2 for our horizontal asymptote, x equals 1 and x equals negative 1 for our vertical asymptote. So we know that f is even. Here's our first derivative graph marking our local maximum at x equals 0 and our concavity graph. And we're going to put all of these together to sketch a graph of this function. So let's go ahead and put our vertical asymptotes in at x equals 1 and x equals negative 1. And we can put our horizontal asymptote in at y equals 2. And we can put our point at our intercepts in there at x equals 0, y equals 0. It's actually the point 0, 0, and that's going to be a local maximum right there. And now let's try to graph things. How can we make this function concave up from negative infinity to negative 1 and have it be increasing? Well, that means that it must follow this kind of a shape. It must be increasing up to infinity, going up to that asymptote. And then how can it be increasing and concave down? Well, this shape right here is how it's increasing and concave down. It's increasing at a decreasing rate with a little bit of a downward curve, but it's still increasing. And then it's decreasing concave down right here from 0 to 1. And then from 1 to infinity, it's decreasing concave up. And that looks like a function that's decreasing more rapidly at the beginning and then kind of levels out as it reaches this horizontal asymptote. And if we take a look at the Desmos graph of this function, we can see that it's pretty close to what we got here. Of course, the computer is a lot better at graphing these things, but the idea is that just using calculus, we can get a really good idea about how graphs behave, which are really important for doing analysis on functions later. And that's all we're going to do for this video. We'll do the next and last example in another video.